Open Space started as a collaboration with Linköping University. We received NASA SMD funding along with 27 awardees beginning in 2016. This is the website. We're basically concentrating on dynamical simulations, interactivity, and SPICE mission visualization, code browsing, multi-platform, and also we are natively from the Hayden Planetarium, so planetariums, and globally linking them. These are our partners: Adler Planetarium, Morrison, Houston, North Carolina, Gates in Denver, Air and Space, and I also put Boulder as well as Exploratorium, who are new. We did this in 2015 when we encountered Pluto. This is before NASA funding, and we did a international 12 site international collaboration to view what was happening at the moment. And we were interviewing scientists. My student, Michael Marcinkowski, who did this visualization, is over on the left in those images, or the movies where we saw the scientist interviews. In a post-case scenario, once the images were returned, these are the SOC images that came in as JPEGs. But with the SPICE kernels, we're doing NASA SPICE visualization to actually look at the planning for missions. And then we also worked with ESA data on Rosetta, as we can see here. So we want to do the image projection onto the models. And in this case, near perihelion, you can actually see the outgassing and the rotation once we put all the SPICE together and the image projection. And also after our NASA funding, it allowed us to beef up and have this collaboration beyond Linköping University in Sweden with University of Utah and NYU. What we're seeing is the eclipse here, sort of a hard shadow case, but over the Tetons and showing our atmosphere and coming in with the globe browsing over Earth. But also I spoke of networking, and so here we see actually a remote presentation that I drove from the Hayden Planetarium basically to the Pleiades conference, which is our national sort of planetarium conference, where I was driving people over Mars. We're working at the University of Utah on touch screens so that we can have large screen displays like this in museums. Here is, we're coming in on Mars and our globe browsing features. What we do is put together multiple resolution images here so that we're actually in the terrain modeling. This has been done by high school students using the NASA AIM stereo pipeline in the background. This is University of Arizona's terrain modeling of Mars with the high rise down to 25 centimeter resolution that we're able to fly over. There are 500 sites at this resolution that we're able to put out. We're also working with Emily and Brian with the Trex to be able to pass data products back and forth. And so here we're coming in on the Curiosity landing site, and this was the USGS anointed high-rise mosaic. And here we can see the SPICE positional information for Curiosity. And we're over Pahrump Hills here, and we're going to come in even closer in just a second. And here we are coming in over the navigation camera terrain models that we're taking actually the point clouds derived for driving the rover off a NASA Planetary Data Service and then skinning that and projecting. To come even closer, Robert, please, hello, and, we're coming in even closer to 4 times the resolution and also in color, which we'll see here in a second, projecting the Mastcam images on top of the navigation models. We do this all interactively, all in real time, free and open source for the world. And then also we've been working with, from the very beginning, NASA Goddard's community coordinated modeling center for space weather research. And we're also getting help from Horace and his group. So what we're doing is interactive visualization. This is a little bit low resolution because this is from a YouTube 360 stream that accompanied this. We're doing volumetric rendering and also taking the field lines out, and this is temperature mapped to field lines as we see from the model in this case. What I'm not showing is the digital universe, which Jackie touched on yesterday with putting Gaia data into this, but a cornerstone of what we did at the American Museum of Natural History to put together the entire universe at all scales. This is natively multi-scale, so we could cruise the entire scale range of the universe with something called dynamic scene graph. There are a number of academic papers that are coming out of this because we work with essentially these internships with the university, Linköping University, University of Utah, New York University, to publish papers about this visualization process. So in a nutshell, that is open space. And I'm doing a demo a little bit later. One thing I should mention, Charlie Duke, Apollo 16 lunar module pilot, was in our dome on October 20th. And for an hour, we flew him over the landing site with his wife and his 2 kids, are about my age, mid-50s. And so we were able to take Charlie back to the moon, but with his family. He left a portrait famously on the moon. That's on YouTube if you want to know about it. It's in 360. Contact me.
Okay, questions for Carter? Yes.
Hardware recommendations for open space?
NVIDIA, latest, within the last 2 years. Oh, by the way, also I am carrying for the demo. I have a couple Mac installs if you want, and so just see me in the demonstration. Yes.
So what is the real install time to get a simple side dome up and running? You want to do is that a lot of work?
So we're using something called the Simple Graphics Cluster Toolkit, which was an open source, basically tiling methodology for multi-synchronized displays. And so far, the way we've been doing that is to have our lead developer, Alexander Bach, who's doing his postdoc at NYU, to actually contact the individual facilities. John here in Boulder is about to do this on a Skyscan system. We have, by the way, we have letters of support from Evans and Sutherland, Skyscan, and SCIS, as well as the Illuminati. So we're trying to cover all ground so that we can install these on planetariums all around the world.
Do we have any questions from online? Who's monitoring the online?
Nobody's awake yet.
Certainly on the East Coast, they should be awake by now.
Yeah.
Other questions in the room?
Or
Do you have any more events planned? I mean, where you coordinate, I know the Pluto flyby and things like that?
We do, and in fact, Pluto, who could deny it? So we were able to get the whole world, basically, all continents except Antarctica, but we did hear that one person was watching McMurdo, so I guess we had all continents. Yes, for the upcoming Mars landing in November, we're going to be doing that, and we're going to do that in coordination with eyes in the solar system. We're looking at coordinating sort of a backplane from open space, so that we're going to be working on, some mission-specific things. We also have other events planned. I'm sorry, it's a little too early for me to remember the specific dates on that.
All right, thank you, Carter.
Thank you.
Our next speaker, Jonathan Fay, talking about Worldwide Telescope.
So Worldwide Telescope started out as a collaboration between a bunch of people who met at AstroViz a little over, I think it was about 13 years ago, and started talking about the concept of putting together a storytelling and visualization engine together. And so out of that, the project started its genesis in MSR and Microsoft Research, and we developed it as originally as a huge multi-panel demo across a big power wall with a cluster rendering, and did that as a demo. And then that was our first version of Worldwide Telescope, and eventually we moved to a storytelling engine on a desktop machine with basically high-end hardware requirements that basically was the highest class gaming machine at the time. Eventually we also moved into cluster rendering for planetarium domes. Dinaj and Mark and twisted our arms, and I think Morrison was our first installation. So we also had a number of support for planetarium, from the inflatables to the brick and mortar planetariums. And the visualization was the sky, from radio all the way to gamma rays, and virtual universe. but the fact that we had this built-in tour authoring environment allowed people to share with each other, and so you could create visualizations on the desktop machine and bring them into the planetarium, and that was a pretty good story to be able to actually share that. And then we had kiosk mode, so people could build kiosks with a little bit of Photoshop, a little bit of data put together, and put together a nice kiosk with a touch screen or something like that. And so this ecosystem started growing. Microsoft in 2013 started the process of handing this off to open source, and the American Astronomical Society and the .NET Foundation took over it. So AAS is now doing the management and continued development, but .NET Foundation is managing the open source side of things and owns all of the copyrights and patents on it. And under that, one of the things that we wanted to do is, that's great, but all these school districts, all these people, they don't want to have these huge downloads and administrator privileges and always a Windows machine. So what happens if we create a version that can run on a phone and author something that you can then play back in a planetarium? So under the AAS, we've actually created a version of Worldwide Telescope. We still support all the planetarium modes and the desktop modes, but we also have a full version that includes the universe, most of the universe as was displayed in Worldwide Telescope, and by the end of the year, pretty much feature parity. So we now have solar system orbits, the entire minor planet center, going out to slow and large scale structure of the universe, and we can do some crazy things like actually editing a tour. And I just decided to do this at the last minute, but I'm going to load Mark Subaru's Cosmic Wonder. I happened to find it on a flash drive, and this was designed for a full dome planetarium show at Adler, and we actually can bring this in here and play back the tour, go through editing on it, and load this in, and basically work on the same tour that was running this planetarium show. And so the ability to bring in all the same data layers and things like that, FITS files and all the data visualizations that the same desktop, all in a web browser on any platform, is really opened it up to the whole AAS constituency. We're hoping that we're to partner as we're finishing up the sort of what we call feature parity, to partner up with IPS to start moving both of the platforms forward to really kind of integrate and get back to focusing on the full set of features across planetarium and web. So I'll go to questions now.
Perfect.
And worldwidetelescope.org will get you right into the web client.
Questions for Jonathan? Yeah, Travis.
How often are the FTC objects updated?
About every 3 or 4 months, maybe, but you can update them yourself in the desktop client. You can update them yourself as often as you want. But we don't want to. We could have like a daily process to do it, but it's a pretty big file, so we want people to not be having to download it every time they launch. So.
Other questions? I have a question.
Sure.
You talked yesterday about the tile resolution format. You said that's going to become standard. In trying to work with it, I haven't found a good standard to work with and such. So are there tools to help us get those tile resolution images into WWD and such?
Yes, John.
John will be doing that. Are you up next?
Chills, yeah.
All right. Well, any questions from?
Whether you intended or not.
I didn't intend it. Any questions online? We still have a minute left. All right, we got a question back here.
Real quick, so the Worldwide Telescope desktop version is offline, or we have to, like, if I want to bring a laptop to a classroom, for example, and do Worldwide Telescope, but I don't want to use their internet. How do I?
So you can load and play back any data that you plan to see ahead of time. And John Grunsfeld asked me this at Long Beach because he wanted to make a tour, for the shuttle mission. And so he went through this thing. Oh, what if I can't run Windows? What if I can't do this? Well, you can load. While you're on the internet, you can cache everything you need to, create the tours, play it back and everything, and then you can just unplug the network cable and do the same script over again, the same tours, and it worked perfectly.
Is
you
that
can
cache
also
persistent?
save the cache to a thumb drive and hand it off to someone else who can load it and then play back all the same things as well. So we built the system a few years ago so that we can hand these out to like people in the middle of nowhere with no internet who've never seen it, who have a low-end laptop, and they can just load this in, and it has the software, the tours, and a subset of the data. But being online is the best thing because there are literally petabytes and petabytes of data connected to WWT, and you really want to be able to stream that in as you fly. But as long as you're playing back the same script, we're caching everything you see.
All right, and is that cache persistent across browser instances? If you close the browser, does it lose the track of the cache?
So that the desktop version is the one that works on that.
Okay.
The browser version does require a persistent internet connection because the browser caches are not really very predictable.
Okay.
We're hoping in the future to do a little bit better on that, but
Yeah, the
if
desktop.
you can't connect to the internet with your browser, it's kind of hard to
All right.
go completely offline.
Thank you again. All right, John, what do you, didn't read your talk. Montage Image Mosaic Toolkit.
Yep.
Oh, fantastic. Yes, this is
What you need. So
Sorry, I'm not at my laptop.
See, how do I start this?
what are you in?
Just need to start a slideshow.
Okay, so go slideshow.
There it is.
There you go.
Oh, yeah, okay. Okay, so yeah, this is not going to have any moving parts, so it's going to be very boring compared to the last couple of talks. We're about building the content for things like WWT or a planetarium show or whatever, for taking raw data and turning it into the kind of stuff that you then show. Good. So if management asks, I went through these slides in detail. You're impressed with our pedigree and the range of applications that Montage has found and all the projects that are using it.
Can you turn up your volume a little bit?
Do I have a volume? My personal volume?
Personal.
Okay, bellow mode. Montage is a set of command line tools, library, Python modules, but basically a set of atomic, reproject this, coadd these, that kind of thing. We started off as Unix-based tools, but we've cross-compiled. So there's Windows app executables. We've created a Python binary extension module, and we've even had some of the modules cross-compiled into pure JavaScript, so they run in the browser. In fact, the little image down here was made using DS9, which is the JavaScript version of DS9, and it does the reprojection in the browser. The data and the reprojection are done in JavaScript. By the way, every image that's hiding around in here was made with Montage. So again, one task for each module, which makes it very easy to script, makes it very easy to put into pipelines, to use in things like Python. It was first and foremost a reprojection engine. Take a bunch of images, reproject them, coadd them, but you also have the issue of dealing with background levels. In astronomical images, the backgrounds are the one thing that tend to float around a lot. And in particular, something like the 2-mass H-band data If you just take the raw images and co-add them, you can't see anything. Well, you can pretend you can see the galactic center there. You have to match the backgrounds, and that's, you don't want to just flatten everything, because a lot of times there's structure in the background that you want to keep, galactic plane. So that once you've done it, you get something like this, which is still looks horrible in some ways because of the air glow in 2MASS, but certainly is much more interpretable. Just to drive that home, there are three example papers here where getting the backgrounds right was critical to doing the science. Also makes much prettier pictures. We've done a lot of work also in terms of real visualization. You can once you've got final images, you can make you know, full color mosaic composites, JPEGs, PNGs. Don't forget you're doing this in any projection you like. We cover everything that anybody uses. And we also have quite a bit of functionality for doing overlays. I mean, in this case, it's almost all overlays. This was something done for the Kelp project, where they wanted to see where their data, which is in yellow and mostly looks green, overlapped with TESS, which is in blue and mostly looks green, and the Kepler and K2 fields. There is one little bit of image data, which is the galactic plane in the infrared. If you want to build really large stuff, you need to use high-end computing. You need to use a cloud. You need to manage the process. And so one of the surprises we had was the extent to which Montage is used as an exemplar application for the IT community doing workflow management. This is an example of a project we did in collaboration with USC, which builds one of these engines, and Amazon to do a large-scale set of mosaics for the galactic plane. Okay, so need to get this in to remind myself that the users are key here. They'll tell you what you need. Basically, now you can script anything you need. And my closing message is that if you see something you like, you can build your own copy of it. You can build your own version of it. It may be the wrong projection. It may have too much extra garbage added. So you can go out and find the original data and build what you need for your purposes. So.
All right, questions? Jonathan.
So John, if I had a very large data set like you know, all sky imagery or anything, and I wanted to have that in a tile multi-resolution format, say toast, for worldwide
for
telescope,
instance, yeah.
I use Montage to do that.
Why? Yes, you can. We have a set of tools specifically for toast building. You build the mosaics. If I start with a lot of little images, you can't necessarily build one large 1 arc-second resolution image of the entire sky. You could, but you wouldn't be able to do anything with it. So you can do all the reprojections, get the backgrounds fixed, decide what you want the stretch to look like, and then you can feed it into a set of tools that will build the pyramid that Toast uses. In fact, you can even translate something like hips into Toast using Montage, because we have those two projections are what we added to WCS, dealing with heel pigs and dealing with Toast.
Other questions here? All right, so I have a question. If I were creating a VR 360 movie and I had 6 walls of an environment map, could I then project it out to, say, on all sky, longitude, latitude, equirectangular projection?
Yes. Oh, yeah.
Something like that? Or
sure.
do hemispherical dome master?
Yeah, even if you needed to do like an offset.
So the planetariums could use the software to project for their dome masters.
Yeah.
Yeah.
Can you say a little bit about when Toast would be optimally used versus the HIPS format?
I've always thought that HIPS was actually a better thing for dealing with coverage maps than as an image projection. It's kind of a strange projection. Well, toast is a pretty strange projection too, but it's specific to the application. HIPs with the funny rotation. It's actually two real projections, but it's kind of hidden. I think
I ask because, you know, HIPs is being adopted more and more widely.
Yeah, it's easy to translate back and forth, so I don't think there's any real reason to, if you have a specific application that uses specific software, just translate it that. I don't think it's one over the other, really.
Okay, thank you very much, John. Okay, I'm the next speaker. My talk is Cosmic Pointillism. And is this working? No, it's not working. I have to use this. All right. So brought to you by NASA's Universe of Learning. And Pointillism is the painting style exemplified by Georges Seurat, who took this 10-foot by 6-foot canvas and covered it with tiny dots, lots and lots of tiny dots. It was a very masochistic painting style. In my background, I have a lot of dots in my background from my PhD thesis doing SPH simulations of galaxy formation, which then got actually translated to appear in the IMAX film Cosmic Voyage. I like to joke that my PhD thesis was nominated for an Academy Award. But this render was done by Lauren Carpenter's software from Pixar called Star Render. It's a custom software. So when I tried to do my own visualizations, I naturally started trying to use RenderMan, and I wrote a RenderMan shader to do best stuff, and it didn't work because RenderMan is not well suited to do transparent things. Anthony Apodaca of Pixar told me it took 70 hours per frame for this snowstorm scene in Monsters Incorporated. I used a variant of it called Blue Moon Render Tools, which was a ray tracer. That got me better, but I still broke it with my cosmology simulation. This took 29 hours. And about 10 years ago at an AstroViz conference right here was the first version of my own code called Splat Particles, which did that same scene in 27 minutes. So I've been writing my own code since then. My latest version of it is called Pointillism. It, based on points, sorts the points in 3D and uses the painter's algorithm to paint them on the thing. It can do stars and clouds. And let me give you some examples. This is a galaxy collision, all right? We can do that via n-body and SPH simulations because the hydrodynamics is smooth and the gravity is softened, so these are point clouds. If you show them as points, it looks kind of ugly. If you use that SPH shader that I talked about to represent the projected spline kernel that's actually calculated in the code, you get a lot more detail in the gas. You also get a lot more detail in the stars so that you can get a galaxy collision. If you add into it some Hubble images of various stages of a galaxy collision, you can produce a visualization that starts with the Hubble image, goes to the simulation, lets the galaxies collide in the simulation. One of them just sort of buzzsaws through the other. But if you stop it again here and rotate it around, you can see at this stage you matched a different Hubble image. All right, turn time back on in the simulation. The tidal tails develop relatively quickly. And at this point, we've matched a third Hubble image, showing that the Hubble images are just one snapshot in this billion-year-long galaxy collision simulation. All right, we can also do stars. This is Akira Fujii's Orion. If we take the Hipparcos catalog and we take a point spread function model with 13 parameters, and with 13 parameters, I better be able to fit things. So you get Gaussian for the core, exponential for the wings, add in colors based on the temperature, or the black body temperature. You can roughly reproduce what Akira Fujii has. But that image on the right, the visualization, is actually in 3D. So we can put these things together and rotate the constellation in 3D naturally using just the stars of Hipparcos, right? And see how the constellation changes, yes? Furthermore, you can, if it rotates around, you will notice that Betelgeuse up here is very faint. Why? Because proper 1/r² dimming is included for free when you're doing this whole thing in 3D. Put those stars and clouds together and you can do nebulae. For the Orion Nebula, we started with a Maya model, which is, of course, just a hard mesh surface. We need the points to generate from them. But if you use Maya particle generation, you end up losing particles at the convex corners because Maya does its particle generation based on surfaces. Instead, we take that mesh,
We throw a bounding box around it, and we volume generate the particles so they're evenly distributed in volume, not in surface. We create what we call a nebular layer cake, where we have an opaque layer beneath the surface, some soft clouds on the surface, and some wispy clouds above the surface. And the cut through looks like this. You can see there's a dark background, and then it gets fuzzier and fuzzier as you go up. That produces our view of the Orion Nebula. And then for the fun, you call up your friend Robert and say, hey, Robert, let's do that for the infrared version from Spitzer, which is much larger. All right? And then you can do a visualization like this, which we released in January of this year. Flying into the infrared, as we cross through the veil, we switch to the visible light, get down to the surface, and we see the big valley, and watch as the valley opens up as you're seeing the infrared, which is a deeper layer inside the nebula. We fly into all the stars that you can see in the infrared, and we go back to the visible light. A lot of those faint stars disappear. They're not seen in the visible light. And we come through and pass by a hero proplyid that passes right by the camera. All right, final slide. I'll do a demo next session with the VR 360 on Oculus Rift. You can fly through that in 360. The videos are available on YouTube, our Hubble Space Telescope channel. If you want to download the videos and even the frames, Hubble Site Videos Science and the Orion Vis-IR dome frames were completed this month, but I didn't have time to post them before I came here, so they'll be completed by the end of June. Otherwise, my monthly report to the Universe of Learning will be deficient. All right, and there's my contact. Thank you. Questions for Frank? Yes.
What's the next? Are you evolving this to other things you haven't got to in the Pointillism you want to evolve, or a tool that you just want to apply to a bunch of?
I want to take first. I would like to. I spend part of my time writing code and part of my time doing the visualizations. And so for each new project, I try and choose something that there's something interesting to add to it. What we're going to try to attempt next is a Crab Nebula. I don't know, as we've got the full data to get the Hubble stuff together, it's still iffy on that. We're also, as you know, working with Eric Whitaker on various projects. We're going to see if there's something interesting we can do for that as well.
Hold on, I've got one question here, and then we'll go to that.
Well, Cameron,
Go.
ask your question.
Yeah.
Is Pointillism meant for part-based data set?
It's designed around point-based data sets. It's not a generic. It doesn't use grids. So when I did an AMR, I actually filled all the AMR grid things with points and then visualized it. That's how I did the Supernova 1987A. And that was fun, actually, to be able to use the AMR data.
Kyle.
What are your frame render times for those dome frames that you put up?
The longest ones lately have been about 30 minutes per frame. For the VR, sometimes I have to do some ray tracing, and that can add another hour to it, just because I have to do near-field ray tracing to get the VR one done right.
Back there?
The time is per CPU or in a cluster?
It's one. That's one CPU on one machine. I run parallel renders of different frames on different cores on the same machine.
Have you tried this on the GPU?
I have not tried doing. I tried long ago doing it on GPU, and the computers ran fast enough that it didn't. It was more work for me to program it, and I want to do the science and the visualization. So if I had a student who could do the GPU programming, I'd love it, but I don't.
With that simulation that you showed us flying through the Orion Nebula, how much of that, how do you get the proplyid in there? How much of that was added in after that?
There are Maya models for the proplyds and the disk and the jet and such. And actually, the proplyds were actually rendered in Maya using particles, because I was able to do that cleanly through that. But everything else was rendered through Pointillism.
Where did you get the Maya model?
The Maya model was constructed at Space Telescope. Greg Bacon is our Michelangelo of Orion. He sculpted it with assistance from Massimo Roberto and other folks who Orion, as well as myself. Yes.
The proplyds looked very much like our model from AV2018.
Yes, they did.
So yeah.
Yes, we definitely got. I was up at AMH when we created that. So right. So yeah, we.
Yeah,
well,
it's after you left, but actually.
No, it was 2000. It was our first show.
Yes, but with the construction of it, the proplyds and the shocks look very much like our model was released in part.
Okay.
So, okay.
Hey, let's give Frank a hand then.
Okay, who's next? I didn't. Okay. Thank you. Okay, Alex Gurch on Firefly and interactive particle visualization. Oh, that's not. There we go.
Excellent. All right. Hello, everybody. My name is Alex. I'm a second-year grad student at Northwestern. And I want to share with you a little bit about Firefly. It's a web app that I've been developing in partnership with Aaron Geller, a member of the visualization group at Northwestern. So Firefly is built in WebGL so that we can visualize particle datasets straight within the browser. And so my research is focused a lot like Frank's was on galaxy formation simulations using an SPH-like code. And so here I'm showing an example of running Firefly on one of our simulations where we start kind of zoomed really far in on the galaxy, turn on the dark matter, and then we can see this sort of filamentary structure of the cosmic web. And so this is much sped up, obviously. So that's pretty cool. So Firefly has a lot of other sorts of features that you can use in it. So we've implemented filtering. So there's a pre-processing step where you can translate your data. So Firefly will work with any sort of particle-based, or I guess any three-dimensional data. If you have an array of points, you can put it into Firefly. You can tag columns as being filterable, as well as we have an RU student who's adding in additional functionality to color individual points by some sort of column. You can also plot velocity stream plots or any sort of vector quantity right within the app, all still interactively. So that's pretty cool. And so these movies that I've been showing you of Firefly are all running with somewhere between maybe 10 to 20 million points. And then I'm going to show you at the end something really cool that we've also done with it. But I always get asked the question, why build something browser-based? It's like, what is the point? And I think it really comes down to one simple thing, is that if you make it browser-based, it's super easy to distribute. It's like kind of cross-platform for free. And with just a URL, you can share it with somebody in the public or a collaborator or something. One nice thing as well, because we're using WebGL and we do this translation step to a JSON format, you can alter the user interface as a set of configuration files and attach that all together. And so you have sort of your app state and the data all packaged together, and you can share it super easily just by web hosting it. Of course, the con to that is that you could lose performance, or there could be like logistical issues and like hosting such large data sets. That's a thing. But so far we haven't really run into anything. Our major limitation has actually been RAM, is how much of the particle data you can store in your local memory. So the nice thing about doing it browser-based as well is that if you have the HTML file, you can embed it as an iframe from within a Jupyter notebook. So this has been super useful for me doing my analysis. I'll be typing away in Python and I'll be confused about like the perspective or something, or if I'm looking at the right projection, I'll be able to open a Firefly canvas, right in line, spin it around, get a better idea of what I'm looking at. And all of that comes for free, all the same version of the code. All I have to do is open an iframe. So I really like that. As well as sort of final argument for why browser-based. So I'm not the only person thinking about this sort of thing. This group put together an interactive browser-based particle visualization thing. So as a science gateway to access their data for their public data release, because the size of the data set made it such that it wasn't feasible to just distribute normally. You can't just go download it. It was like terabytes and terabytes. And so having an interactive explorable tool so that you can filter the data and take only what you need can be really powerful and actually science enabling. So browser-based, I think, is going to be the way to go for that sort of thing. And I'll leave you with a bonus here. So I've loaded in 2 or 3 million particles from Gaia DR2, exploring interactively. This is all on my MacBook. And you can try this out as well if you'd like by visiting those links. I can post in Slack. There was another link before as well. Thanks.
Okay. Questions for Alex? Yeah.
Does this have, I mean, this looks a little bit, I mean, YT has some similar capabilities. Is this like a web version of that or some relationship between the two?
So I'd say that they sort of fill different spaces. So my understanding for YT is that it's really useful for volume rendering, and I'm sure that it has some particle visualization abilities. But yeah, I would say having the web platform is really unique, and that's the real strength.
Cameron's about YT.
Yeah, he's right after.
I can address some of those things, but what he says is absolutely correct. YT does not operate in the browser, and that is a huge strength to what they're doing. So I'm really excited about this.
All right, Jonathan.
So what language do you develop in? Do you do it straight JavaScript or do you use a transpiler?
Yeah, so it's all in JavaScript. Yeah, HTML, JavaScript. There's some D3 JS in there as well. So that's the nice thing about using JavaScript is that the user interface is all generated from the config file. So all the divs that you see on the screen in Firefly are generated adaptively. And JavaScript lets you do that.
So yesterday they mentioned Party View from AMNH, which is a similar type tool, but it's not a web-based tool.
Right.
So could the Party View type data sets be pulled into this?
I think pretty easily. It would be as simple as writing a wrapper that would translate into the JSON format. And then Firefly would be able to read it, no problem.
I think that would be an excellent, yeah.
Yeah, it's beautiful.
Yeah, so we have like 3 or 4 Jupyter notebooks already for how to translate the Gaia data using SQL queries, and then our simulation data. But it's super simple. It's like once you have it working once, then you run the pipeline on your data, and then you have the JSON files in the exact same format, and then you're able to host it somewhere, and it just works.
Okay. Any questions from online? You're monitoring it back there? No, no questions. All right, let's give them another hand. Thank you. And Cameron, are you up next, or is it? Oh, I'm sorry, Wolfgang. Sorry, I was jumping to the YT. Wolfgang will be talking about yet more 3D modeling using software called Shape, right?
This I need to have on the other side. Okay.
There you go.
At least we make it. Great, this works. Good morning. I'm going to present Shape, which is our sort of 3D modeling and visualization software, and is in fact a kind of an interactive 3D laboratory for astrophysics. And here you can see one example which is my tag thing, image, my badge image, which I have in my pocket. This is a simulation of a star-forming region where you have it's a generic region where you have the dust cloud, which is illuminated by 4 different kinds of stars. Scattering is all computed physically, radiation transfer, and you have a mix with one jet that was actually simulated with the hydro module in Shape, and another jet that was made with polygon modeling, as is done in other kind of software. The software was made to do something like this. You have an observation of your object that is kind of scrambled in a projection that we have on the sky. It's actually 3D, but kind of, well, squashed together. And the job is to reconstruct this in 3D so we get a better idea of what this beast is actually like, and we can classify it or interpret how its life is going on, which is the job of the theory and some story that is behind it, how the object lived, evolved, and is what kind of community is living in, which is the theory that we want to get about this. So this is what this was designed for, and here's are a few examples of stuff that we did, mostly for visualization. Most users use it for reconstruction in 3D using images and kinematic information that comes from spectroscopy. This is not just a visualization tool, it's really astrophysics. But lately we're using it for this kind of stuff. And one important feature for future development and usage is shown here at the bottom, where you see a transition of a rendering going from the optical, where you have scattering dominated and opacity dominated images, and going gradually towards the infrared, which is getting more and more important since infrared astronomy is so important, and for delivering what is different in one and the other. This smooth transition may be important. That cannot be done usually in software like Maya or other visualization software where you can do complex structures. Here's an example that shows a smooth transition where you go from a disk, a dust disk that is opaque in the optical, and then go to the infrared, move your spectral scope to the infrared, and you see how it becomes transparent and changes color. And the jet is actually a hydrodynamic simulation and has only one spectral line, so it changes color as you move the range and disappears. This is how it works. Basically, similar to 3D Studio or Maya type of software, you build your models with polygons, do also sorts of manipulations and modifiers on it, so it gets the shape that you want. This is scaled up in time factor of 2 only. It takes 3 minutes. I'm told I have 2 minutes, so I'll skip forward. Here's a preview region where you see the volumetric rendering in preview. You use some textures to modify the mesh, for example. You have many tools to get the structures that you want. Here you mix two of them. So you can very quickly build stuff. All this took only 7 minutes, now compressed to 3. I'll skip on. This is the preview in 3D, volumetric. Then this is the rendering mod. Well, go back. This is the rendering module where you have access to the kinematic information. This is a position velocity diagram on the right, and the image is on the left. And so you can use this for scientific modeling or teaching or whatever. And I skip on to show for Maya research, it is important to have channel maps. This is the channel map module where you get the channel maps for this object. All this was done in 7 minutes. So I'll keep going. I'm done. Okay, just to finish, you can do teaching and playful simulations. Somebody asked me, can you do a rocket engine? I said, no idea. It took me 15 minutes to set up the simulation. And this is a exoplanet light curve simulation, just to give you an idea of the range of stuff you can do just in one package of software. No programming by the user, nothing. No scripting, anything else. So if you like it, get your astrovisualizations in shape.
Question, yeah.
Well, you'll also be able to demo it for people who are interested downstairs. We'll give you the information later. But I do have a question. How does it treat emission lines? Does it treat emission lines?
Yes, there are several ways you can do that. Can compute it from there's an atomic line catalog that you can use for computing it from the density, temperature, and so on. Or you can just set it yourself, just artificially. There are many ways of calculating the emission.
John,
how do you get a hold of the software?
You download it and run the installer. and then ask me how it works.
Typing shape into a search engine might come up with a lot of different things.
Yeah.
Is there a tag we can throw with that?
Yeah, astrophysics, 3D, whatever, and then you should find it or ask me about it. I can.
Or add it to the Slack thread too.
That'll be good.
On Slack.
Okay.
Yeah. What sort of a hardware recommendations does it have compared to normal 3D modeling?
You can run it on this, or you can run it on. I recommend to have a lot of RAM and for parallel computing, so it's faster. You use as many cores as you have. If you want to do hydro, make it big. You can't run it in batch mode, so you really need a workstation for it.
All right, thank you. Cameron is now up next to talk about YT. And you're in Keynote, right?
Yeah.
Beautiful. Awesome.
Okay. So yeah, I am primarily a computational astrophysics researcher, but as part of that, I'm a member of the YT open source community. It sounds like some of you know about that. It's a Python-based piece of software that was originally developed for visualizing and doing analysis on computational simulation data. Over the last 10 years, there are now on the order of 50 or 100 developers who've contributed to it at some level. There's a large community and a Slack channel and a mailing list where people are very responsive. So if you have a question or whatnot. So as I said, it was originally developed for doing hydrodynamic analysis, hydrodynamic simulation analysis, but it's been generalized to deal with any real volumetric or multivariable data and a variety of different file formats. It runs in Windows, Mac, Linux, Unix, so on and so forth, and can output to a variety of different formats as well. So traditionally, it's dealing with volumetric data, either grid-based data or particle-based data, SPH, AMR, moving mesh, what have you. I'm going to talk about some of its capabilities. So you can do raw slices through your volume two-dimensional slices. This is just an example from a sample data set looking at an edge-on view of a galaxy and density. And this was the code that was used to generate that in Python. So it's really straightforward to use. There's obviously a lot of tweaks and annotations that you can do in your images, but at a base level, it's very, very simple. You can do projections like the one that's on my badge here. This is the FIRE data set of a Milky Way mass galaxy projected in density. So we're doing a full projection through a three-dimensional volume. I should also note that there's been a huge amount of development in the last year, led primarily by Megan Lang, Nathan Goldbaum, and Matt Turk on treating particle data much more natively, as opposed to previously we would deposit particle data to a grid structure and you got some grid-based artifacts, but that's gone away now. So it's much faster and easier to deal with particle-based data, and it looks a lot better. And this was the code that I used to generate this particular image. You can also do volume renderings, so where you get to play with the transfer function that you're actually projecting through an image. This is a volume rendering of a large-scale structure simulation, and you can see the transfer function is such that going from purple to yellow, you're going to higher density. And we're looking at different isodensity contours. And so you can see that the yellow stuff is in the regions of highest density where filamentary structure and large-scale structure intersects, and you see the clusters and so on and so forth. There's also an interactive volume rendering tool that you can use on your machine. Oh, I also didn't mention that YT is fully parallelized and can use MPI on as many cores as you want to use it on, so it scales very well. But yeah, you can do some of the stuff like what Alex was showing with Firefly, not in the browser. That's something that's awesome and something that YT probably will never be able to do. Thank you. But yeah, it uses hardware acceleration, and you can interact with your volume renders in the browser and flip them around and so on and so forth. But it's pretty memory intensive. It was also used for nature cover a few years ago with ALMA data, so it doesn't just deal with X, Y, and Z coordinates. This was in the case of X, Y, and wavelength or velocity in Z. and it provides a bunch of different ways of viewing different types of data sets. In addition, you can make movies. So I was just showing how we would make individual images, but you can scale those together by moving your camera around or by changing the underlying data set. This is a volume rendering of molecular ALMA data. This is a simulation of a large-scale structure box, and it's showing over the evolution of the universe how the initial overdensities in perturbations in density go nonlinear with gravity and start to form filamentary structure and so on and so forth. But again, this is all generated with just projections where you slide your camera view around. Similarly, you can project in a variety of different fields. Previously, I've just been showing density, but this is showing density and density-weighted temperature. The circle represents the virial radius of a galaxy, again, this Milky Way galaxy, as it grows with time over the evolution of the universe. And obviously, you can see a lot of structure. So part of it is going to be dependent on the simulation data set or the underlying data set that you're using to generate these images. But the YT community has a number of sample data sets that you can use, or you can go on Slack and just reach out directly to simulators or other scientists about using their data sets. People are usually pretty happy to have them shown in other venues. And finally, you can also do spectra. This is with the help of an additional code that's open source that's built on YT called Trident that I'm the main developer for. So this is just generating some spectral features as we send a slide through this two-dimensional slice. This is the silicon 2 feature at 1260 angstroms that we're looking at, and you can see the development of this spectra. So for more information, check out yt-project.org. It's fully open source. It's all free. The installation's pretty painless. It's done through Conda, and yeah, I can take questions.
Questions? Yeah.
I mean, this is also just a general question for all the people who've done with their software. How low have you applied software in terms of grade level? Have you actually given this to high school students that here, play around with it, see what you can do with it, just to encourage more to go to visualization?
I've worked with some high school students with this, not general purpose classrooms, but high school students who've come to Caltech and been interacting with our group. Certainly college students are appropriate for working with this, but I guess it's all dependent on how much coding experience they have, because primarily, aside from the interactive volume rendering, this is all coding and for that purposes, because it was originally defined as a research tool.
Yeah, and I only ask because JPL just had our open house, and I had tons of high school kids coming up to me and saying, how can I get into this realm?
Okay, let's bring that question up to the rest of the speakers in the general discussion. Okay. All right. Yeah.
Same question as the previous guy. What are your frame render times for some of these really intricate volume?
Oh, so for the really intricate volume renders, you're not going to be doing this in real time like the work that you're doing. It's primarily you connect to a supercomputing cluster where you actually have it and render it for your films or whatnot.
Sure.
For the movies that I'm showing, I rendered those, like the Fire Galaxy simulations, in parallel on 64 cores. I did that in like a couple hours, I think.
That was my next question. You said it runs all on MPI. So
yeah.
I was going to ask how many more.
Yeah.
Other questions in the room? Martin, any questions online? Okay, I have a question. How generic is the camera motion? Could I export a camera from Maya to get a cinematic feel to the camera, which is one of the main limitations I found in scientific software?
We are working on that right now in terms of building camera paths, taking keyframes that you can put together and have a line that connects these various key paths. But I should talk to you afterwards if there's a format that you can, like a generic format that a lot of people use for doing this sort of thing. Okay. I would love that.
Okay. All right, let's thank him again.
All right, next up is Powell. Let's see. That's you, right? That's right. All right, there we go. All right, Powell Burnham.
can't pronounce your last name.
Okay, I'll do it myself.
Biernacki, right?
Paweł Biernacki, yes, close enough. If I knew that the picture on the badge would be better than I have yesterday, then that would be my background, which is a galaxy cluster that I simulated with a Ramses AMR code. And I'm going to talk to you about, well, making movies or images out of the simulations running live and out of the cutting edge product that we are actually using to publish papers. And actually I should switch the VR into 360 degrees as it was pointed yesterday. That's not the same. VR would be more interactive than the regular 360 degrees movies. So Cameron gave you a little bit of introduction of what the data structure hydrocodes can be. So you can have grids or you can have particles. Here I'm dealing with the grids, which are connected in a very funky way, where at the given level we have also the smaller cells or neighbors of the larger level, the larger cells. The code that we are using is highly parallel, and as I said, is used for hydrodynamic simulations of everything between star-forming regions to cosmological simulations. And we have the 3D information about the density, temperature, metallicity, velocities of the gas, and so on and so on. And we also include, of course, stellar particles, so not single stars, but stellar particles, and dark matter particles. So currently the code is about 1,200 lines of Fortran code because the general code is also Fortran. So that is being called every few steps when the code is running. So we are outputting the movies while the simulations are running themselves. For particles, we check where the particles fall into the frame, while for the grids, we try to deposit the desired quantity in a mass-weighted or density-weighted fashion on a grid, which would then create an image. So we use it initially for debugging, and as you all know, that the black holes are red crosses in real life. So that was a black hole in the galaxy. Of course, there are some problems in the simulation, so that was a fantastic way to see what's going wrong. This developed into something more advanced, where we can look at different quantities of a galaxy cluster of information and different epochs from the density, temperature, star particles, and the dark matter distribution. Then we moved to 2 eyes because we started rotating our cube finally. And well, if we can rotate it, then let's make a left eye and a right eye. And again, the same thing in the density and temperature. But now let's leave the vantage point of the god and let's move back into the inside of the cube in which everything is happening. So what I'm trying to do is use the rectangular projection to basically trace line of sight for each of the angles that we have in the box. This is a bit complicated because even at the low resolution, we get about 100 million points that we need to calculate, and this is anyway much lower than what Google suggests of 8,000 by 4,000. And then, of course, another eye. So instead of taking few seconds per frame, we are taking about 5 minutes, 5 to 10 minutes. Doesn't really work for particles. I have an idea how to do it for particles, but maybe you have a better idea here. This is how it looks like when we project the gas for the whole box. And if you actually want to see it, I crossed the organizers and I forgot to apply for the talk and try session or whatnot. But if you want to find me to have a look at the videos, please do so. Otherwise, I'll also post the links on the Slack channel. Thank you.
And congratulations for finishing early. So we have time for questions on this. In the back.
Where have you exported your content so far?
YouTube. Just YouTube. That was the easiest way to actually find a way to play it on my phone.
And have you worked at all with their new, what is it, EAC?
No, format? I've never heard of it. Yeah.
Other questions? Questions online? Okay. I can't think of a question.
It's all right.
Good. All right. Give me a hand again. All right. And for the folks online, we have a special bonus talk that I was told about at the beginning of the session. George Jirogovsky from here in Caltech I have no idea what you're talking about.
You'll find out soon.
That would spoil the surprise, Frank.
Hold on.
Let's have the VNC here.
There we go.
Nope.
No. We need tech help here to hook up his computer. He's got the USB-C
with VNC connector. Oh, here we go.
I found it. I thought we had one here.
All right.
Oh, there. And then, oh yeah, and then the DVI into that.
And then the DVI into that. There you go.
Excellent.
Thank you. You must work for some high-tech company or something.
I'm a Mac. You can put your laptop on top of this laptop.
Looks like.
So, ladies and gentlemen, George Dragowski.
Wait. I can't see what I'm doing here.
Well, not yet. Okay, so it's sending it to there.
Yeah.
Okay. And if you hit play.
Well, there's no play.
Oh yeah, you have to move your cursor onto that. Over that way. Getting it. There we go.
All right.
Yeah.
There you go. Now you get.
Wow, thank you.
All right, now we're ready.
So lots of people think about astronomical data visualizations as pictures of stuff on the sky, and we'll do a lot of that. And that's of course crucial for all outreach purposes. But most scientists actually don't care about that. We quickly turn pictures into catalogs of properties of things we see in the sky. And then we need to visualize data, which is a whole another story. And data visualization has to be included at every single step, from just looking at the raw output of the instruments, every single step of cleaning, preparation, choice of algorithms, experimenting with different algorithms, finally understanding what our algorithm is telling you and presenting results to someone. And so by and large, I'm going to talk about visualizing complex data spaces. And that, I think, is the single biggest bottleneck of data science today. Because the problem is not that the data are big, but that they're complex, and complexity is often expressed as high dimensionality of data space. Like in a catalog like Sloan, there are hundreds of dimensions. If you do data fusion, we're now talking about data spaces with thousands of dimensions. Biologists are talking about tens of thousands of dimensions. And how do you see interesting structures that may be present in such spaces? So unless you can somehow visualize things, you cannot understand them. And there is no point in getting expensive data unless you can discover knowledge in them. And so any technique that can help us see more dimensions of the data space is a good thing to have. Turns out that humans are not limited to 3 dimensions. With different tricks, we can display up to a dozen, or we can display as many dimensions as you want, but we can understand up to 10 or 12 when looking at the pseudo 3D graph. So this is where virtual reality comes in. And first I'll point out something: multi is not 3, and multiple 1D or 2D plots are not multidimensional plots. VR is exploding on the scene. It's the next computing platform, following the sequence from mainframes to desktops to mobile, and now this will be the next thing. And so we'll have to learn how to use it, but it's also a really good thing. It solves many problems that plague traditional desktop type 3D of occultation perspective. There are good reasons for this. There are many studies have found that fact of immersion really performs magic, that if you are embedded in the data space, if you're inside the data looking out as opposed to outside the data looking in, you get a much better intuitive perception of the geometry of the data and see things that you couldn't see otherwise. And there are concepts called proprioception, essentially using yourself as a ruler to judge the geometry of the data, and kinesthesia, using your motion in the data space to give you a better idea of the overall 3D distribution. It's also a natural way to collaborate, which is a really useful thing, and everybody who's tried it loves that to do that. The best of all is we don't have to pay for it. This is based on zillions of dollars of investments by the game industry. This is why there are these
miracle devices like headsets. They're getting better and better all the time. And so the question is, how do we use it for scientific purposes? We actually experimented with this kind of thing since 2008 in this experiment called Meta Institute for Computational Astrophysics, where we found it's really powerful platform, even a primitive tech at the time, for anything collaborative, interactive. But also, we started playing with multidimensional data visualization, where scientists can walk into their data, interact with the data and with each other. Since then, we continue to do this as the new tech was coming along, and that went to intermediate programs, use called IVs and so on, and there's desktop version of it. But now that has led into a startup company from Caltech and JPL called Virtualytics, which is producing a system that you will soon get free academic licenses for, where basically multiple users can be embedded in the same virtual data space, interact with the data with each other and with machine learning. Because this is really a crucial point, that you always interact with machine learning algorithms as well as visualization, and you just can iterate this again and again. So there'll be a demo of this after the break, and I invite you all to try it, because you just don't get it until you really try it yourself. You see the real subjective advantage of VR immersion once you're inside the data spaces. We're also now continuing to play with creating virtual teaching labs at our center at Caltech. Essentially, 3D gives students perspectives on things that they just couldn't get from the traditional visualization points. They can do this anytime they want. And you can shrink yourself to the size of atoms or to the size of galaxies. And you can also do things that are either impossible or really dangerous to do in real life, like an explosion in a virtual lab doesn't kill anyone. And so we're learning how to do this best, how to do proper interaction between humans and virtual displays. So with that, I'll stop. I'll take any questions, but I really encourage you to go and take a look at the demo. Thank you.
Okay, questions for George? So when you say you're doing multidimensional data spaces, I mean, we're still limited by the 3 dimensions of the virtual spaces, but then you can add in color and size and shape. Correct. And everything.
That's right. You play with colors, transparencies, sizes, shapes. You can put textures on data points. We're now playing with sonification. The data are singing different tunes where you have more dimensions in acoustic space. But the point is that you just can't wrap your mind over more than about 10 or 12 with some practice. 6 or 7 or so is really easy for most people.
Right. So
get started.
It's adopting the language of traditional print graphics in terms of trying to layer a lot more information onto it. But now you're given the 3-dimensional virtual space to work in, which is really
right. So
cool.
in addition to the 3D part of it, there is this strange new magic of immersion that we're so optimized to interact in real 3D spaces, so that really works better than any traditional flat screen where you spin things around and so on.
All right, over here. Yeah.
If you had 6D phase space information, could you watch them evolve in real time?
Absolutely, yeah.
Does the current version leverage the multi-user technology?
Yes, yes.
Okay, right.
I've been promising this for a long time, but you know how it goes. Takes longer time than you think. But truly, within the next couple of months, I think, anybody will be able to download a free version for the academic world.
Fantastic.
Yeah.
Yes, of course.
Yeah, a couple of things real quick. First, I absolutely agree with you about the issue of data analysis rather than just simply looking at the original data. I think the biggest missing piece in a lot of the visualization software, a lot of the visualization approaches is they don't address the issue. Like the researcher has to ask questions of the data and has to do it right then. And just you don't get discovery just simply by looking at the original data. You have to do all this analysis.
Right.
But my question for you is, in sort of another direction, have you ever seen the large, like 100-screen hyperwall that they have at NASA Ames?
Yes.
Because one of the things I was impressed with there was the ability to do this multiple dimensions on multiple screens that were correlated to each other. So you could look from one representation to the other and see how they correlate.
Absolutely. The advent of sort of consumer electronics VR tells you that for a couple $100, you can do what you can do with a multi-million-dollar hyperwall or a cave. So that's what's going to be really useful. You don't have to go anywhere. Everybody will be able to do this in their office or airport lounge or wherever they want.
Well, my point though is not that so much as the difference in representation between being in your data and having to map all these dimensions in the same space, as opposed to having multiple spaces that are correlated. So you can look
I see what you're saying.
Then you can say, well, what about this? You could circle something in this representation, and then you could see how it plays out in another representation at the same time. So multiple representations, even in the same virtual space, because there is a limit in any one virtual space as to how much you can perceive at a particular time.
Sure, you can have as many virtual displays around you as you wish, and infinite in virtual space. But it turns out also that VR is a really good thing for data fusion, that you can combine more effectively multiple data sources in a single display as opposed to the multiple displays that you have to look at. And we're trying to quantify this in proper fashion to make a real numerical statement. Why is this better?
Well, I will say, the one last thing I'll say about that is, I was approached by my management a long time ago to say, can you give me any specific examples of scientific discovery with visualization? And I don't think there are very many documented examples.
Let's take that offline afterwards, all right? Because I know we have 2 questions online, Gordon.
One question
online.
George from Sarah Price. Have you been able to create a consistent library of astrophysics data sets to use in VR for scientific exploration and teaching?
Well, it's in progress, I should say. We're doing it for our own sake, but yes, we will make it all public eventually. Because actually, not just astronomical data sets, but other types. Because this is kind of data science skills that people need everywhere. And it doesn't matter whether data came from gene sequencing machine or sky survey.
All right, let's thank George again. And we have a few minutes for general discussion. Now, you asked a general discussion question already, so why don't you re-ask it? And the speakers can answer.
Yeah, so this is for all the people who've done with software. What kind of educational scaffolding have you created for people to jump into your software? How low does it go? Have you thought about broadening that? And just, I'm looking for it as an educational tool, because again, I get kids all the time coming up and saying, how do I get into this? Or how do I do stuff?
I'll approach that first. I'm the programmer, I'm the user, I'm the only person who's ever used my software. So Pointillism is not built for others to utilize. I had one graduate student come in and use it. Cameron?
We have pretty extensive documentation with a cookbook of different recipes on how to do various different visualizations, along with the sample data sets that we can download to do that. But still, as a base level, yeah, we've tried to be as welcoming as get people started with our docs and our Slack channel for being able to interact with the community, but for giving it to like elementary school students and so on and so forth, it can be challenging unless they have some experience with programming.
Which some do actually.
Some do.
Yeah, some do.
Okay, so with open space, I didn't mention that we have online YouTube tutorials. We're going to be expanding that. We also have wikis on GitHub where you can go if you want to obtain the code and go deeper. And also, I'm very interested with working with the Museum Alliance to basically exercise open space for what it was designed for, as a platform for researchers to sort of have interviews and that allow them to take us through the data sets. And so that's really sort of in line with your mission. So.
And Jonathan?
So while the AAS is not specifically doing outreach or education work with WWT directly, it's more aimed towards research. As over the last 10 years, WWT has a lot of individual groups that have basically adopted WWT for their educational, from all the way through, K through 8, middle school, high school. The country of China represents one of the largest worldwide telescope user bases, and they have a whole Chinese curriculum for students based on World Telescope. And so the Worldwide Telescope Ambassadors program that does work with, I think, middle school. And so there's a lot of use of it. The way that we layered the software to be able to be accessible to people fairly broadly, but then sort of right-click menu into the deeper features meant that you could sort of ignore the really super professional features and just kind of use the interface. And so we sort of designed it to sort of transition between those audiences.
Did you want to address the question, Alex?
Yeah, so when we were building Firefly, shared in the beginning, the idea was sort of have maybe 3 or 4 different user types or audiences. So I've used Firefly personally to lead like tours and simulations for 10. Although we have like open sessions that but also the idea was to allow the user interface to hide all the complicated features that you don't really need if you're just trying to tell a certain story. If you're trying to build a narrative, you give the users the freedom to interact how you want them to. So you sort of simplify the experience. That's all configuration files, as well as the idea you want to generate a subset of these that we would then share with the teachers or something to help lessons centered around something towards that's the freedom, limited interactivity.
And that's just all there for GitHub.
Yeah, it's on.
Okay. I think Ken was the one who mentioned that NGSS is all about authentic science experiences now, where there's no reason to dumb things down for kids anymore. You can just show them the tools that we use.
Right. NGSS is really built on experiencing and acting like a scientist. So utilizing visualization software is an excellent example of putting NGSS into action in astronomy. And using George's software, if they could learn that in VR, that would also address the tech component of STEM as well. All right. Do we have any questions online for the roundtable discussion? All right. Any questions in the room? Further questions in the room? What would you like to see out of visualization software like this? Yes.
I have a general, I guess, question. It might be just too simple. I don't work with large data sets very often because I realize that you have multiple different formats to be in. Do all of these softwares, will they take all the same formats? Or are we seeing that some of you prefer certain formats over other formats?
Jonathan? There are so many different formats for looking at data. For instance, WWT has all these GIS formats that we also support for the Earth viewing. And in space, you have VO tables, you have people who just have like tab delimited files.
Carter was talking about the SPICE data.
Bits files, SPICE kernels.
HDF.
There's so many different formats in science and things like that. Supporting them all is very difficult. There are some tools like TopCat that allow you to do transformations and processing data. So for instance, if you use TopCat with WWT, you can take data from a lot of weird data formats and support it and then convert it into VO table and then load it into WWT or other VO table compatible software.
It's the great thing about standards is there are so many to choose from.
Yes. And so we should make one new one that will take care of it all.
So I will say that the first thing I do in most every project is figure out the data format that I'm going to use and translate it over to a data format that I can pull into my code. It's just something I've been doing for decades. It's a standard part of the process. Janice? Question, Jackie.
It's a worldwide telescope question. I'm curious about how the relationship between worldwide telescopes and you ends up coming together. Maybe you could comment on it. So that would be, from a scientific perspective, seeing that happen was really exciting to watch that kind of third-party interaction, and I'd love to see it with open space as well.
So the part of people ask me a lot of questions like how much data does World Telescope have, how many users do you have? And a lot of these questions, if I knew the answer, we would actually be a lot less successful than we are. The fact that we don't have a huge budget. There are many projects at CWWT that literally have 20, 30 times the budget that project has now for keeping it together. Part of the fact that other projects basically said, well, let's integrate glue, let's do this for this project, let's connect WWT to Astropix, let's run a whole bunch of planetariums in China on WWT with their own curriculum, customized version of it from GitHub, translations with local constellations and things like that. We never would have had the budget to do those projects. And the fact that it's decentralized and that people can say, I can use part of this, and that you have an open source environment where you can both collaborate and help people get started on it, but then they can just take it and go with it. And so I think that's the real power of open source and the power of being able to have everything you have available on GitHub and putting all your data out. And sometimes it's messy, Blood planetarium companies who check out the code, did lots of changes to it and never contributed back, and that's going to happen. The community is not always going to behave, but you get lots of delightful things that happen that you never would have expected and you never intentionally organized, but there were good outcomes that happened. So I can't tell you necessarily how the process is other than open it up and let people play with it. Support what you can.
All right, so I was intrigued to see the Jupyter integration. So I wanted to ask how many people in this room use Jupyter notebooks? Okay, they've become sort of de facto standard amongst astronomers and such. Does anybody want to talk about the Jupyter integration of their visualization tools? Because that's, the amount of code you need to write for a Jupyter notebook is really pathetically simple. So yeah, go ahead.
Yeah, a lot of the YT is fully integrated with Jupyter Notebooks. A lot of the documentation.
You want to explain what Jupyter Notebooks is for the half of the audience that doesn't use
sure.
it?
Jupyter Notebooks is a platform for executing Python in your web browser in a series of different kind of cells where you can execute a little snippet of code, and then it will show you the result of that particular snippet once it's executed, then go to another cell that builds on the previous cell, and so on and so forth.
It's sort of like you're debugging your code as you're writing
it.
It's kind of like Mathematica.
Yeah, Mathematica. Yeah, exactly. It's like Mathematica or something like that. And yeah, YT is fully integrated with that, and you can output those notebooks and put them in a web viewable form and that sort of thing, and a lot of the documentation in YT is done for that.
Yes.
Orion Telescope is also working on a version that's integrated with Jupyter Notebooks as well.
Exactly. Thank you.
What I do is I work on a version that you can either use in an interpreter or in a Jupyter Notebook, and you can build towards sort of similarly to the web version, but instead through scripting rather than doing everything out by hand. So.
And this is a lot for the publishing aspect of WWT being used in AAAS publications.
So in the future, it could be used for abstracts that are tours, do whatever being talked about in the papers or that sort of thing.
Okay. Any other comments or questions? All right, it's 9:59, so we're going to finish a minute early for you, Robert. Okay, you can get us back on time. Give all the speakers a hand.